Thank you for coming to my Pass the Hash talk. Interested parties that were called out on the meeting invite might be Blue Team supporting Windows sysadmins, or anyone who wants more exposure to Windows. And I will supply the slides after for serving as reference, and I know Darian is recording as well. All right, so what is Pass the Hash? It's a long-running attack that abuses authentication weakness in Windows operating systems. Essentially, an attacker could supply a password hash rather than the password itself to gain access to a resource. And why you should probably care about that is if an attacker gets the password hash, they can authenticate as a user without cracking the user's original password. So you can think of this as a token with an unlimited lifetime. And there's a little caveat that, well, this no longer works when the user changes their password, but they don't change the password unless they're told to, or they have reason to believe it's compromised. For a little fun fact, I suppose, on how long this has been going on, this attack was first published in 1997, so it's been a little while. And despite the meme here, stealing tokens aren't unique to Windows. Being able to use the same token on every single computer in your environment is particularly bad, so I couldn't help myself. All right, so we're going to do a brief explain like on 5 on password hashing. I don't want to get too much into the weeds here, but when you store your password locally on your machine, it isn't actually stored in plain text. Your system hashes it. And so essentially what this looks like is your password goes into some magic function. We don't need to care about what that looks like right now, but a hash comes out, and that's a one-way function that is in theory not reversible. And you can crack this hash by brute forcing the key space until you have a collision and 2 different password hashes match, or it doesn't even have to be a password hash, 2 different hashes match. There's a few ways to optimize breaking this, namely using a dictionary where you can hash every single word in a dictionary and compare it against each other, against the stolen hash. And does it match? If so, like I got the original password. And the stronger your password is, the harder it is to crack. So that's really the takeaway here. And for the math buffs on the call, hashing is like a exponential function, and cracking is logarithmic. So one is significantly harder to do than the other. So now we're going to talk about the SAM database. Security Account Manager Database. I can never say it right, but for the Linux peeps on the call here, this is your Etsy shadow on Windows. This is where all the users and groups are stored in the database. It also acts as a cache for domain users. In enterprise environments, you have a domain, and so that has a frequent tie-in here. Password hashes are stored here, and there's 2 types. One is LM hashes and the other are NT hashes. LM hashes, you don't really need to worry about. It's really legacy. It's horrifying, really. This is like your NIS accounts on Linux. So in 2021, you really should not see this. I fingers crossed, hope you never encounter this again. But whenever you hear something called NTLM, that is just the affectionate term for NT hashes. There's a little bit of imprecision of language when talking about Windows hashes, but those are generally referred to as the same thing. So take that with a grain of salt moving forward. Biggest thing to note is that these hashes are not salted in the SAM database. And if you're not familiar with what a salt is, it's something that adds entropy during the hashing process. And you can actually see the image in the bottom right. You can take the same password with different salts and get different outputs. And that's something that's probably a good idea when dealing with passwords. That makes cracking it quite a bit more cumbersome. So this SAM database is actually hooked when doing authentication, either local or remote users. And the equivalent on domain controllers is something, it's a specific file. It's called ntds.dit. We just call it the dit usually, kind of a bizarre name, but yeah. Biggest takeaway from this slide is hashes are not salted. All right, I'm not even gonna try to say this service. We just call this LSASS, all right? LSASS is this process on Windows that handles authentication. So whenever you do a password rotation, login, and it's also the service that sent like logs auth events to the event viewer. This does all of that stuff. It also talks to WinLogon, which is another process. We're just making sort of a head nod that it exists. That's something you have in Active Directory for the scenario where the user's uncached. All right, so now we're starting to get to the meat and potatoes here. So if you're an attacker, your objective here is to extract caches. And there's a bunch of tools out there, one of which probably the most popular is called Mimikatz. That's what I have a picture here in the bottom right. Mimikatz leverages a specific, we call it like token on Windows, but a specific privilege called debug privileges. You don't really need to, fixate too much on, well, what is a debug privilege? The main thing you need to understand is debug privileges is what you use to be able to dump hashes from an access control standpoint. And by default, if you have local administrator, you have debug privileges. And so assume if a local administrator account is compromised, they can dump hashes every time. Now you can break that in some ways. I've yet to see that in real life during pen tests that I've done. But as an attacker, you can go to a bunch of different systems, start dumping hashes, create a list of all the users you come across and their associated password hashes. Again, they're not salted. So if a specific user has the same password as another user, you only need one of those hashes, then you can try to spray it across the whole environment. Another good thing to know here is in Windows, by default, the last 10 users that log in are cached. And so essentially what that means, if there's an attacker in your environment and they dump the hashes, they get the last 10 users that log into that machine, whether it be domain users, local users, service accounts. If you have like a help desk admin remoting in, they get that hash as well, and they can escalate their privileges across your environment very, very easily. And just sort of anecdotally, speaking from my own experience doing pen testing, once you essentially get that initial foothold in the network via sending a malicious email or perhaps doing a Windows exploit, like the rest of it is just past the hash, really. Like it's essentially game over once, with few exceptions, but once you get that local admin access to dump hashes, that's it. Back in the day, between like Windows 7 and then Windows 2K12, Mimikatz actually was able to extract passwords from memory, and a lot of times they might even be clear text. That's been patched since then, so you don't really need to worry about that. But Mimikatz is like the industry standard tool for attackers here. All right, so getting to the password authentication workflow for Windows, I've really simplified it here, and we're actually going to not really talk about number 2 right now, but essentially, a user's logging in, they want to access a resource, there's a challenge response. We can kind of skip past that for the moment, but essentially the client sends the username and hash. A lot of times your computer is doing this on your behalf. I don't know a single person on this call that knows their password hash on Windows, right? It's just software that's doing it on your behalf. The other server you're trying to connect to or the workstation or whatever, it compares the hash you provided against that hash that it has in its SAM database and says, does this match? If so, we're going to give it access, give this user access. If not, then, access denied or wrong password, what have you. Where you can take advantage of this is essentially if that layer of software is handling the hashing for you, like you can be a bad guy and you can steal a password hash and then just provide that. You don't need to go through, the additional steps of hashing the password that's being provided or anything else. The destination computer in this scenario is none the wiser. They don't necessarily know that this hash has been compromised. And in their eyes, this is the expected workflow. The only difference being is the hash was compromised. So what are the implications here? Well, I sort of let the cat out of the bag a little bit. You can use this for privilege escalation, lateral movement. If help desk admins remote in to help an end user and the end user gets their account compromised, you can essentially or should assume that help desk admin who most recently, one of the last 10 users to log into that machine, they're also compromised. And they have access in a lot of cases to all of the workstations. And so suddenly, from a isolation standpoint, this gets very, very tricky. But password cracking is not required to inherit all of the access that this user has, and they just masquerade as another user. You can then take all of your stolen hashes, spray it across the environment for multiple user accounts. If everyone has default Uber password 1, then there's bound to be a hash in there that is that. And if you're really an ambitious attacker, you can try to crack that password in the hopes that perhaps they use that same password for a web app that is perhaps not domain joined or something of the like. So there's a few interesting areas there. This works like a token without expiration. The compromise hash can be used regardless of how good the actual underlying password is. So you can have the world's best password, but if your hash is out, it's meaningless. So looking at this diagram, my glorious diagram here of how this might look in an environment, I'll sort of step you through it. So you usually have some initial exploitation, phishing email, Windows exploit, what have you. Local admin gets compromised with malware. Attacker then uses that local admin rights to dump the hashes from the SAM database. They retrieve all the local users, cache domain users, etc. They add that to their master spreadsheet thing, where they're staging out all of this from. And then using those compromised hashes, they can do a pass the hash attack to gain access to other machines. And, it sort of just goes down the line. There's no fixed number of hops or anything like that. They essentially gain more domain privileges, secrets on disk, users with debug privileges, etc. And that just keeps going on and on and on. And you just repeat steps 2 and 3 until either your objective is complete, or the attacker finds the domain admin hash, or a process running as domain admin for that matter. And yeah, so that's the other thing. With debug privileges, you can actually hijack other running processes. So I'll get into that in actually the next slide. But yeah, that's why isolation is certainly super important. If it's a domain joined machine, then that's pretty much game over. A lot of times you actually find that standalone Windows machines are actually more secure than domain joined ones, but that's a rant for another day. So we can take a real life example of what we just saw on the last screen. Local admin Sally clicks a phishing email, gets infected. They dump the SAM database. They pass the hash to another secondary machine. Windows comes with a built-in administrator account. A lot of times in environments, that password is the same. And so you can pass the hash to a local account. And that's what line item number 3 is. And then the attacker might find on that second machine, there's antivirus running as domain admin. And that's a no-no, because you can hijack that process. And now the attacker is domain admin, and then it's game over. And this might seem like an extreme example, but I've done this during a pen test, and that pen test lasted an hour. So you never really know what you're going to find in internal pen tests. All right, so now we're going to talk about the challenge response piece that I skipped before. This is what is referred to as net NTLM. And so I tried to color code it because I realized this might be a little challenging to read here. But everything we talked about up until this point, think of that as like within the orange brackets. That is the NTLM hash on disk. And then, when you want to talk to a server, they give you a challenge. You essentially append that to the hash that you already know, and then you hash that yourself. You pass that over the network, and then they have the challenge and they have the hash that they were expecting, so they can follow the same format there. This is adding a little bit more complexity here, but that's why I wanted to separate it out. Make sure people have a pretty good understanding of how the core authentication works. So when you hear like NTLM v1, NTLM v2, it's actually shorthand for net NTLM v1 and net NTLM v2. This specifically happens for remote authentication, happens behind the scenes for domain joined systems or by an attacker's toolkit after stealing hashes. This introduces a new complication, something called NTLM relaying. And what happens here is you can essentially trick a domain joined machine into sending you a net NTLM hash, which you can then just pass it over the network to another machine. The only restriction is you can't pass it to the machine that sent it. But there's tools out there. One is called Responder, and there's also Mpacket, and they leverage MBNS spoofing or NetBIOS spoofing. By default, NetBIOS is turned on Windows. And in the event that, maybe this is for another talk here, but it's essentially you can trick another computer into sending you a hash. So if there's interest, we can talk about that another time. But there's, again, no need to crack these hashes. You sort of just proxy it on over and you get access to something else you want. So now we're going to talk about some mitigations here. There's a lot of potential options. The most obvious one is probably like if you think you're compromised, change the password. But where this can get kind of hairy is like, it's not just the user whose device it is. It's probably like all recent logons to this machine. Some ways to detect pass the hash abuse is like excessive SMB connections to multiple systems from one host or user. Definitely, like this is probably the biggest one. The limiting of local admin sprawl across an environment, like if users don't actually need local admin to do their job, they probably shouldn't get it. And if they do require it, they should probably get 2 accounts. It should be like a standard user for logging in, and then a second one to escalate to with that local admin rights. Somebody can certainly make the argument, well, that's really, annoying or complicated for the process. But if we look back, most of the scenarios where literally you just lost the whole domain comes with the person who's actively using it is running as local admin. They click an email as local admin, things of that nature. So that's probably the biggest one. Using LAPS for break glass accounts. LAPS is a Windows process, I guess, tool. It stands for Local Admin Password Solution. It's actually put out by Microsoft, and it tracks all of the built-in local admin accounts, sort of the, this machine lost connectivity to the domain. I can log in to that account to rejoin them. That's why it's a break glass account. What this essentially does is it will set all of the local admin accounts in the whole environment to something sort of random, something unique, so that you mitigate pass the hash on a local level, like local account user level. It works similar to Kerberos. The machine tracks and rotates the password based on policy, and the password stored in AD, and you can have all sorts of access controls on who can access the passwords from AD. The real thing that sysadmins like about this is it doesn't require additional servers. You can sort of just use it with existing infrastructure, and you can certainly monitor for break glass usage. It depends on your environment and the appetite for something like that. Another one, because we talked about you can hijack processes. If you have a lot of people who RDP into a jump host, setting RDP timeouts and enforcing the end of the session is super important, because if you think about it, if that host is compromised and everyone's logged in actively, that means there's far more accounts or processes to hijack. An attacker can cherry pick what has the most access and let me start using it in their context. So that's a really big one. In disabling or reducing the cached credential count. If you remember, I said it's 10. That's the default. A lot of times, perhaps 2 is appropriate in the case where they need to be able to access, a user needs to be able to log in without internet access or something like that, or even 1, it really depends, or 0. But 10 is probably too much for a lot of environments. All right, we got some more here. So I have to shamelessly plug Credential Guard and Secure Boot, more Microsoft stuff. I have to give Microsoft a lot of credit. They've done a lot of security stuff in the last 5 years. Very, very impressive. So what Credential Guard does is it stores that LSAS process, that authentication process, in a container and turns Windows 10 into a hypervisor, and you cannot dump hashes. It breaks Mimikatz indefinitely. So that's really a huge one. Secure Boot, they sort of go hand in hand. This validates signatures of boot software, drivers, OS, all that stuff to ensure integrity. Now, this is what's super important about Credential Guard and understanding. People think this is the silver bullet to breaking past the hash. It's actually not. It removes the ability to dump the hashes, but doesn't stop past the hash. So if your hash is already stolen, a Credential Guard enabled machine will do nothing to say, no, that's been compromised. So this only really works if the entire environment has Credential Guard. As soon as you find that one system that doesn't, you might have wasted a lot of the attacker's time, but they can still get through. So anyways, yes, monitor and restrict the use of domain admin accounts logging into anything beyond domain controllers. Local admin account, or sorry, domain admin accounts really shouldn't be used to administer servers for the same reason. They should sort of be in their own tier. Domain admins only log into domain controllers. No one else can log into domain controllers, things like that. Essentially, the standard server admins should get like control of their own GPOs, not domain controller GPOs. And the reason being is if they can set a policy, they can have a script run on a domain controller, and then you just lost your domain controller. So there should be isolation beyond, is it a server? It should be, is it a domain controller or is it a standard server? So, and the reasoning behind that is the sprawl of admin accounts for logging into servers is usually much greater than that of domain controllers. So there's more opportunity to hijack processes for RDP sessions or what have you. So the fine-grained controls on GPOs is a huge one. And then we're on to our last slide, I promise. So there's a lot of data. So SMB signing is the only surefire thing to stop NTLM relaying. That's the one where you can just spoof things over spoof who you are and then get a bunch of net NTLM hashes. This one is actually very hard for environments to deploy. While it will break net the NTLM relaying, there is a steep performance hit. We're talking like up to 20 to 25% of the CPU. So that is not viable in a lot of environments. SMB signing is enabled by default on servers, but not on workstations. And it would really need to be enabled on workstations to break this. But again, if you're like have a development community on Windows, like it's pretty much out the window. Maybe if like HR or something is on it, you can probably get away with certain pockets, but probably not everybody. Another thing is net NTLM v1 is also legacy. V2 is much better, stronger crypto, harder to crack, adds a timing component. And so the solution is there's a policy. You can make sure that you never send or receive LM hashes or NTLM v1. I've seen in certain environments where NTLM v1 is hard to restrict is when you have like a legacy Linux system that might be domain joined, but doesn't support Kerberos yet, or NTLM v2. I would think most systems can support Kerberos these days, but just to call out there. And then again, if we, perhaps another talk, but disabling NetBIOS in LLMNR. LLMNR is like the next generation NetBIOS, kind of also crap. Yeah, so turn those things off. That's the end of my presentation. I know we have 2 minutes here. I'm happy to answer questions on Slack or bounce ideas back and forth on monitoring and control ideas. I'm sort of infatuated with AD security and Windows security, so feel free to hit me up at any time.